Hello, everyone. I'm Kangning Wang from Duke University. Today, I'll be presenting our work, Approximately Efficient Bilateral Trade, joined with Yuan, Deng, Jieming, and Sivan from Google Research. We have a seller, Sally, and a buyer, Bob. Sally is trying to sell one item to Bob. We consider the classical Bayesian setting, where Bob has a private value V, drawn from a distribution F, and Sally has a private cost C, drawn from a distribution G. We assume F and G are public information, and we assume they are independent from each other. We consider Sally and Bob to be strategic utility maximizers. In other words, they may lie to a trading mechanism in order to optimize their utilities. Our goal is to design a mechanism with good social efficiency. Now the question is, how do we measure efficiency? It turns out there's a natural definition called gains from trade. Suppose Bob's value is V and Sally's cost is C. Then if there's a trade between them, the society as a whole will gain utility of V minus C. Therefore, we can write the expectation of V minus C times the probability of trading between B and C as the expected gains from trade. In order to maximize this expected gains from trade, ideally, the trade should always happen when V is greater than C and should never happen when V is less than C. And that gives us the benchmark called the first best, which is simply the expectation of the positive part of V minus C. We can also define a quantity called the second best, which is the optimal gains from trade from a trading mechanism that satisfies the following three natural properties. The first one is Bayesian incentive compatibility, meaning that the players should have no incentive to lie to the mechanism. The second one is individual rationality, meaning that the players should receive non-negative utilities from the mechanism. And the last one is weak budget balance, meaning that the mechanism shouldn't lose money when it's subsidizing the players. And what we will show in this talk is that the second best is at least a constant fraction, namely 10% of the first best. Now we look at some examples of simple mechanisms. The first one is the fixed price mechanism, where the mechanism first announces the price of P, and then asks for the value V and cost C from the players. And then if the value is at least P, and the cost is at most P, then the mechanism proposes a trade, and Bob pays Sally a price of P to get the item. We can easily see this mechanism is incentive compatible because reporting their true value or cost is the dominant strategy. And also, the mechanism is individually rational because the players won't have negative utilities by participating in the mechanism. And the mechanism is also budget balanced because the mechanism never gains or loses money. So for this mechanism, the optimal gains from trade is simply to choose the max over P of the expectation of V minus C times the indicator function of V being at least P being at least C. Another example of simple mechanisms is the seller pricing mechanism, where the mechanism delegates the pricing power to Sally. Sally will pick some price PC to maximize her profit. Then Bob, seeing the price PC, will buy the item if V is at least the price PC. And if he buys, he needs to pay Sally a price of PC and gets the item. Sally can compute her optimal price PC by maximizing this P minus C times the probability of Bob buying the item. We can easily see the mechanisms IC, IR, and budget balanced. The gains from trade of this mechanism is simply V minus C times the cases where Bob is buying the item. Symmetrically, we have the buyer pricing mechanism, where the mechanism delegates the pricing power to Bob. Bob will then choose the optimal price PV to maximize his utility. Sally, after seeing the price, will sell the item if C is at most PB. Similarly, we can see this mechanism is IC/IR and budget balanced. For a quick numerical example, consider V to be equally likely 1 or 10, and C to be equally likely 0 or 9. We can compute the first best to be the expected positive part of V minus C. For the fixed price mechanism, the optimal price is between 0 and 1, or between 9 and 10. For seller's pricing mechanism, when Sally's cost is 0, her optimal price is 10. And when her cost is 9, her optimal price is also 10. And for buyer's pricing mechanism, when Bob's value is 10, his optimal buying price is 0. And when his value is 1, his optimal buying price is also 0. We can see in this example that the first best is strictly larger than the gains from trade of all these three mechanisms. And that is actually a general phenomenon. In 1983, Myerson-Satterthwaite showed that sometimes the second best is strictly less than first best. And one sufficient condition for that to happen is when F and G are supported on intersecting intervals and have positive densities on their supports. However, even though the first best isn't always achievable, we can still ask if we can get a constant fraction of it. In other words, is it the case that the first best is upper bounded by a constant times the second best? And this particular question was explicitly mentioned in several previous works. In our work, we answered this question in the positive by showing that the first best is upper bounded by 2 times the gains from trade of the seller's pricing mechanism, plus 8 times the gains from trade of the buyer's pricing mechanism, which is in turn at most 10 times the second best. In other words, the better of seller's pricing mechanism and buyer's pricing mechanism, or randomization over them, can give at least a 10% of the first best gains from trade. In our paper, we also improved this constant to 8.23, but in this talk, we will focus on proving the constant of 10. Now we delve into our proof. We assume the distributions F and G are continuous distributions supported on a bounded interval of 0, 1 with positive densities everywhere in order to simplify the presentation. We point out that this is without loss of generality, and our result holds for general distributions. We define μx as the median of the distribution F being conditioned on at least x. We also define mu to the kx as the composition of k functions of μx, and the mu to the minus kx as the inverse function of mu to the kx. Now we present some immediate bounds for our quantities. For the first best, we write out its definition and upper bounded by the second line. We replace the interval of the inner integral from c to 1 to mu c to 1. This inequality holds because mu c is the median of the interval from c to 1 measured by the distribution S, and we are keeping the better half of the integral. And for seller's pricing mechanism, we can write this inequality, where the right-hand side is Sally's profit when she always sets the price at mu c. This quantity is at most Sally's profit if Sally uses her optimal strategy. And that, in turn, is at most the gains from trade if Sally always uses her optimal strategy, because the gains from trade equals Sally's profit plus Bob's net utility, which is non-negative. And similarly, we can write this inequality for buyer's pricing mechanism, where the right-hand side is Bob's net utility when he always sets the buying price at mu to the minus 2v. This is at most Bob's net utility if Bob uses his optimal strategy. And that is in turn at most the gains from trade if Bob uses his optimal strategy. Now we put these three inequalities together and plug them into the thing we want to show. And we will get the last line here. We will then separately deal with the left-hand side and the right-hand side of that inequality. So for the left-hand side, first, we split this integral into an infinite sum of smaller integrals. Then we notice that v is at most mu to the k plus 1c. So we replace v by mu to the k plus 1c. Next, we again split this mu to the k plus 1c minus mu c into the sum of mu to the t plus 1c minus mu to the tc for t from 1 to k. Then we swap the order of summations. And finally, we notice that the inner sum is a geometric series where it's going down by a factor of 2. So it equals 2 times the first term. And we will get the final line here. And for the right-hand side, first, we similarly replace this integral by an infinite sum of smaller integrals. Then we notice that v is at least mu to the t plus 1c. So we replace the first v by mu to the t plus 1c. And also v is at most mu to the t plus 2c. So we replace the second v by mu to the t plus 2c. So it's mu to the minus 2, then mu to the t plus 2c. So it's mu to the tc. And finally, we replace this interval from mu to the t plus 1c to mu to the t plus 2c to the twice as long mu to the tc to mu to the t plus 1c, and drop the factor from 4 to 2. And finally, we copy the inequalities from previous slides and notice that the right-hand sides are the same. So we conclude that we have shown what we wanted to show, and so that first best is at most 2 times stellar spacing plus 8 times stellar spacing, which is at most 10 times the second best. Finally, let's present some related work. For the gap between the first best and the second best, it was shown to be sometimes at least 1.359 by Bloom-Rosen and Mizrahi. And for the gap between the first best and randomizing between Bayer-Spacing and stellar-spacing mechanisms with equal probability, the gap is at least 2.02. And for the special case where FV has monotone Hazer grid, it was shown that if we just use stellar-spacing mechanism, we can get an E-1 approximation to the first best. And for the case where F and G are IID, and more generally, if the median of F is higher than the median of G, then using the fixed price mechanism can give a 2 approximation to the first best. There has also been work on approximating the welfare instead of approximating the Gensburg trade, where the welfare is defined in the following way. If there is a trade, we get a welfare equal to Bayer's value. And if there isn't a trade, we get a welfare equal to the seller's cost. So the expected welfare equals the expected Gensburg trade plus seller's expected cost, which is a constant for any instance. Therefore, maximizing welfare is equivalent to maximizing Gensburg trade, but providing a constant approximation to welfare is easier than providing a constant approximation to Gensburg trade. There has also been work on approximating the second best instead of approximating the first best. For example, in the work of Brosseau, Cai, Wu, and Zhao, we showed that the second best is upper bounded by Bayer's pricing plus Stellar's pricing. And that work motivates us to specifically look at these two mechanisms because they together provide a constant approximation to the second best. And finally, there are more general models such as the double auctions, which is a model involving multiple buyers and sellers. Thanks for listening.